Okay, so from yesterday, Tim taught us about heritability. Bad questions, what extent a given trait's genetic, and more correctly, how much of the differences in a given trait between people in a particular country at a particular time is caused by their genetic differences and how much by their different environments and life histories. So the idea here is that we're partitioning variance in the phenotype by the variance in genetics and in the environment. I also mentioned that we're interested typically in this additive genetic variation, the idea of narrow sense heritability. There's a good fundamental concepts in genetics, several good Nature Genetics reviews papers Peter Vischer wrote. Heritability allows a comparison of the relative importance of genes and environment to the variation of traits. So what proportion is environmental, what proportion is genetic, relatively, is the idea of heritability. And I mentioned some pioneers in genetics and statistical genetics, Sewell Wright and Ronald Fisher, R.A. Fisher. So I'll have abusive notation here in a second. Difference between value of a trait in an individual and the mean of the population. We're just decomposing the phenotype as a genetic component and an environmental component. We can further decompose that genetic piece into additive-dominant interaction. As mentioned yesterday, we often ignore that interaction. And so we've got the phenotype being comprised of additive-dominant interaction, environmental, and error terms. Okay? So if we want to think about this, again, a slight abuse, maybe a great abuse of notation, squaring the deviations of the phenotype from its mean, squaring those deviations of the phenotype of the mean, and doing the same for its component pieces of additive, dominant, and environmental effects, we can then express our variance of phenotype in these pieces. Okay, so a variance of phenotype decomposed into an additive, a dominant, and an environmental piece. We're assuming that the covariance between the additive and dominant effects are zero. Same for gene and environment. So there are tons of complexities in heritability, which is why there is an entire course on heritability in Boulder. Okay, so misconceptions. Heritability is a portion of a phenotype that's passed on to the next generation. It's not half of the genetic contribution to parents are passed from each parent, and each offspring gets its own unique portion of that. High heritability implies genetic determination. Tim, I think, demolished that before. High heritability could be due to, actually, let's take a look at this. High heritability could be due to low environmental variation. Okay. Oh, there's the math. Another is low heritability implies no additive variance, which is not the case. Heritability is informative about the nature of between-group differences. And so again, heritability is a concept that it's a particular population at a particular time. And high heritability implies genes of large effect. Okay, so estimation. Twin studies. You can think about comparing SIB pairs or monozygotic and dizygotic twins. SIB pairs share, on average, half of the same DNA, as do dizygotic twins. Why would one be preferred over the other to examine? If we're trying to estimate heritability, why might we be interested in looking at either dizygotic twins or SIB pairs? They both share half of the genome. What's that? Yeah, go ahead.
Oh, sorry. In utero environment, age effects.
Yeah, so the SIB pairs have a ton of shared environment, but not as much shared environment as dizygotic twins, right? So we're reducing the amount of other variation by looking at these twins. And so, for example, here, if we take a look at that A, D, and E, the additive, the dominant, and the environmental components, for twins that are raised together, they have the same genetic components and the same environmental components. If they're reared apart, they don't have the shared environment. Okay, so we can use these relationships to infer, to estimate heritability. And again, if you're interested in more, I encourage you to go to Boulder. I want to mention, this is what I was going to talk about primarily, because it's what I've done more than using family relationships to estimate heritability. But the genome-wide complex trait analysis program is a way to use unrelated, it's it's a little bit controversial at some level, but it's a way to use unrelated subjects to estimate heritability. We don't need genetic data to estimate heritability in related individuals. We just use their trait variants. But if we want to use unrelated individuals, we can estimate these genetic variance components and the non-genetic variance components with SNPs. So, yeah, I'll leave it there and see if you have any questions. A little cloudy there. Thanks.